This is Bill Farmer again. Welcome to McMaster University course, Computer Science and Software Engineering 2FA3, Discrete Mathematics and Applications 2. We're going to continue with the second topic of this course, Recursion and Induction, and today we're going to talk about orders. We'll begin with a question. So let HA, where H is a set of humans and B is a binary relation H, such that H1A, H2 means H1 is an ancestor of H2. So HA is it a weak order, weak partial order, a strict partial order, a weak total order, or a strict total order? I'll give you a moment to think about it. Okay, welcome back. Now, if this were a weak total order or partial order, this would be true. H would be related to itself. That would mean H would have to be an ancestor of itself, and this is not true for what ancestor means. So that eliminates A, and that eliminates C. Now, if this order were a strict order, that means if we have any two humans, let's say H1 and H2, this would have to be true, or this would have to be true. This would have to mean that every two different humans, one would have to be the ancestor of the other. This is not true. It's not true if our set of humans are, let's say, the set of humans living today. It might be true if H is the set of all humans that ever lived. It might be that all of us have a common ancestor. Okay, so the correct answer is B. This is a strict partial order. Okay, so we're going to talk about several different kinds of orders. The first kind is something called a preorder, which is not actually an order, but it's something that has some of the properties of an order. So a preorder is going to be a set S with a binary relation on S. And let me remind you what this means as a binary relation, that this relation is a subset of the Cartesian product of S and S. So it's a set of pairs. Now, a preorder has two properties. It's reflexive and transitive. And reflexive means that everything is related to itself, and transitive means that if X is related to Y and Y is related to Z, then X is related to Z. And an example of a preorder is a set of formulas with implication. This is a preorder because if we have any formula, it implies itself. And if we have a formula that implies A implies B, and we have B implies C, then that implies that A implies C. So this is a good example of a preorder, the set of formulas with implication as the ordering principle. Now, a preorder can have cycles. If we think about it a moment, the preorder we just saw can have cycles because we can have A implies B, and B implies C, and C implies A. So we get a cycle because A implies B, and B implies C, and C implies A. Because we have a cycle here, we would say a preorder is not really an order. Now, every binary relation on S can be extended to a preorder by taking the reflexive transitive closure of R. So what this means is, if we have a binary relation like this, we can come up with a preorder, which I'll write like this. Let's see, what should I call it? I'll just write like this. And so this would be a preorder. If it is the reflexive transitive closure of R. So this is the reflexive transitive closure of R. So what is the reflexive transitive closure of R? It's the smallest extension of R, the smallest superset of R, that is reflexive and transitive. And we can actually construct this. We can take pairs and keep adding pairs to R until we get something that is reflexive and transitive. For instance, the first thing we would do to make it reflexive, we would add all pairs of this form. We'd add those to R. Okay, so every binary relation can be extended to a preorder. So the idea of a preorder is a pretty basic idea. Another important notion is the notion of an equivalence relation. An equivalence relation is a relation that's reflexive, transitive, and symmetric. So symmetric means if x is related to y, y is related to x. So an equivalence relation is a special kind of preorder. It's a preorder that's symmetric, and equivalence relations are used to determine whether we want to, is a way to formalize the idea that we want to think of things as being the same or being equivalent. Okay, so now let's look at our first real definition of an order. This will be the notion of a partial order. And we can think of partial orders in two ways. We can think of them as weak or strict. So with a weak partial order, we have the less than or equal relationship. With the strict partial order, we have the strictly less than relationship. Now, if you have a weak partial order, you can easily create from that a strict partial order and vice versa. We'll talk a moment about that later. So a weak partial order has three properties. It's reflexive, which we've seen before, and transitive. So it is a kind of preorder, but it's also anti-symmetric. That means if x is related to y and y is related to x, then x must equal y. So that's a weak partial order. A strict partial order also has three properties. It's irreflexive. X is not related to x. And it's asymmetric. If x is related to y, then y cannot be related to x. And it's transitive. And in the slides, I've changed this to put parentheses around this because this property is not actually needed. Transitivity and reflexivity imply asymmetry. Okay, so a good example of a weak partial order is a power set of S. Now the power set of S is all the subsets of S ordered by subset or equal relationship, and a strict partial order example is a power set of S ordered by the strict subset relationship. Okay, so let's just take a quick look at an example like this. Let's say we have S and it equals A, B, and C. So I can show you now, if we look at, we can build up the power set of this. At the top we'll have the set ABC, at the bottom we'll have the empty set, and then we'll have the set of just A, the set of just B, and the set of just C. And then here we'll have the set of AB and the set of AC and the set of BC. So so the empty set is a subset of B, it's a subset of C, it's a subset of A. So we have these relationships, and we also have, it's a little hard to write this, and am I missing one? Oh yeah, we have this too. And then these are all subsets of this set. And there's a lot of, we also have that the subset, maybe I'll use arrows. The empty set is a subset of this, and the empty set is a subset of this. So there's a lot of arrows that we haven't drawn here. So this is a partial order. It is a weak partial order. If we look at the strong partial order that goes with it, it's all the same except we use a slightly different relationship, like this. I forgot to mention in the previous example, I have to get rid of all these lines here. In the previous example, the subset is, the empty set is a subset of itself. Every one of these sets is a subset of itself. Okay, so I've changed it a bit. That's the strict partial order. Okay, now if we look at this partial order, it has no cycles. Why does it have no cycles? Well, if we had a cycle, we'd have this situation. We'd have something like this. And that would mean we'd have this. And then we know that this implies that A and B are the same. So we can't have no cycles. Something that looks like a cycle really wouldn't be a cycle. Why do we get this implication? That's because a partial order, let's say a weak partial order, is antisymmetric. Okay, so what this means is a preorder is like a partial order but has cycles. We can get rid of these cycles and turn any preorder into a partial order. So let's take a quick example. So let's say I have 3 points here, and this is related to this, and let's say I have another point here. Okay, actually I have 2 cycles here. So what I do is I'll create a new order where I have a point here which represents all 3 of these, and a point here, and actually let me draw this a little differently. Let me start over. I made it more complicated than I should have, which might obscure the point I was trying to make. Okay, so let's say we have 3 points like this, and they're related like this. And now we have a cycle here, and what we can do is we can collapse this cycle into 1 point. And now we have, that's our ordering relation. And of course, since we have transitivity, we would also have this. So we have 3 points like this. So by collapsing cycles into single points, we can turn a preorder into a partial order. Now, the one thing about partial orders, you may be wondering, why do we call these partial orders? And that's because we can have this kind of situation. Where we can have, let's say, A and B and C. A is related to B, or we can say A is less than or equal to B. C is less than or equal to B. But A and C are not related. That's why it's partial. Another notion is a total order, and in a total order, we can put every member of our order on a line. These total orders are also called linear orders. And what that means is every member will be on the line, and all the other members will be less than it or greater than it. So that's what we're going to look at now, is a total order. Oh, I guess before that, before we get to total order, I forgot we have a question to do. So let's say S less than or equal is a weak partial order. Then we can say S strictly less than will be the same order expressed as a strict partial order if we define less than from less than or equal in which way? I'll give you a moment to think about it. Okay, welcome back. Well, it's pretty obvious. What we want C. Because we want to say that A is less than or equal to B if A is A is strictly less than B if and only if A is less or equal to B and A does not equal B. So what this illustrates is, even though we started with a weak partial order, there is a total or a strict partial order that goes with it. And likewise, if we started with a strict partial order, there would be a weak partial order to go with it. So if we were going the other way, we'd have to define this, and we would define it the obvious way. We would say this means this, or this. So that means we can go from here to here, or we can go from here to here. So often in textbooks, they don't emphasize the fact partial orders are weak or strict. They just say we have a partial order. And it's often up to the reader to decide whether it's weak or strict. I have focused on distinguishing these two because the properties are different. Weak partial orders have different properties than strict partial orders. Okay, so let's say we have a weak partial order right here. And we have a subset of P. So there's a number of definitions I want to make. We can talk about a minimum element of P. That means it's a member of P for which there is no smaller member. And we can have a maximum member. That's a member of S for which there is no bigger member. It's maximal. Now the reason we call it maximal and minimal is there could be more than one of these. There could be more than one. So let me just take an example. Let's say we had this kind of situation where things are related like this. And let's say the set S was the whole thing. Well, you can see in this case there's going to be two maximal elements. There's going to be this one and this one. And that's because there's nothing, if you're thinking of this arrow as being less than or equal, there is nothing bigger than these two. So they're both maximal. And this would be minimal. And in this case, there's only one minimal element. These two elements are neither minimal nor maximal. Okay, so we can also have maximum elements and minimum elements. So a maximum element is a maximal element when there's only one. If there's only one maximal element, that element is the maximum element. If there's only one minimal element, that element is the minimum element. And it's not necessary to have maximum elements or minimum elements. It's not even necessary to have maximal or minimal elements. So for instance, let's just take a partial order, which you've seen before, which we normally write out the line, the natural numbers, where if something is to the right, it's bigger. If something to the left, it's smaller. And you can see in this case that this is a minimum. It's the minimum element of the whole set, but there's no maximum. And in fact, there's only one minimal element, 0. 0 is a minimal element, and it's the minimum element. There's no maximal elements, and there's no maximum. Okay, so we can also talk about an upper bound of a set, S. So an upper bound is some member, which doesn't have to be a member of S. It's a member that's bigger than all the members of S. And a lower bound is a member that's small of P, that's smaller than all the members of S. And then we can, of course, have a least upper bound, which is an upper bound for which there's no smaller upper bound. It's the smallest upper bound. Likewise, we can have a greatest lower bound. Okay, so let me talk about a famous example. Let's say we have the rational numbers, which is often denoted by, this is called Blackboard capital Q. So we have the rational numbers. We have a whole bunch of these. So forth. Now, someplace along here is a number called the square root of 2, but this is not rational. The square root of 2 is not rational. But if we look at all the numbers, smaller than the square root of 2. Wait, I should say, let's say we're not looking at the rationals, we're looking at the reals. So the square root of 2 is a real number. But if we look at all the numbers, so let's say S, it equals all the real numbers, such that such that R is strictly less than the square root of 2. If we look at all those numbers, this set S has a bunch of upper bounds, like 2 is an upper bound. But the square root of 2 is the least upper bound. It is the least upper bound, and it's not a member of this set. Okay, let's move on. Now we can talk about what I just briefly mentioned before, total orders. A total order, as I said, is a partial order that we can lay out in a line. It has the same, so we have weak total orders, strict total orders. A weak total order has the same 3 properties of a partial order, weak partial order. And it also has an additional property called the totality property that says X is related to Y or Y is related to X. Every 2 members of S are related. And the reason I put parentheses around reflexive is that these 3 properties, from these 3 properties, we can derive reflexivity. Now, a strict total order, it also has the same 3 properties of a strict partial order, but we have an additional property called the trichotomous property. It says that for all X and Y, X is strictly less than Y, Y is strictly less than X, or X equals Y. And so here are some examples that you have seen every day from mathematics of weak total orders, and of course there are corresponding examples of strict total orders. Okay, so one of the reasons we had to review orders in this course is because we want to talk about another kind of order called a well order. So a well order, the way I've defined it, is it's a strict total order. It's a strict total order such that every subset of S has a minimum element with respect to this order. So if I take any subset, any non-empty subset, it has a minimum element. And every well order is Noetherian. So remember, Noetherian is named after the very famous mathematician M.E. Noether. Famous because she was a woman, and at the time she was a mathematician, women were considered not capable of doing serious mathematics. Anyway, every well order has this property of being Noetherian. Noetherian says that there is no infinite descending sequences of this form. So if we start with a member of S and choose a smaller one and choose a smaller one and keep choosing a smaller one, forming a descending sequence, that descending sequence cannot be infinite. So the classic example of a strict total order is the natural numbers ordered by strict less than. So in this case, if we think of the natural numbers, it is a total order. It's like this. If we start anywhere in the natural numbers and then pick something smaller and pick something smaller, we cannot go on forever. Eventually we run out of numbers. That is why the natural numbers are a well order with the normal ordering. Now the integers are not a well-known order. If we think of the integers, let's say make this longer, we have I can start someplace, I can go left, I can go left, I can go left, I can go left, I can go left an infinite number of times if I want. The integers is not a well order. Okay, so there are lots of well orders, and I'm going to show two other important examples. The first one is I'm going to take a set of rational numbers. So my set here is a subset of the rational numbers. And this includes 0, 1/2, 2/3, 3/4, 4/5, and so forth. All of those. Plus it includes 1, 1 and 1/2, 1 and 2/3, 1 and 3/4, and so forth. And if we think of this on the number line, we have 0, we have 1. Basically, we're going to have a bunch of points like this, and a bunch of points like this. And we know that this first group here, that is a well order, and the second group is a well order because both of those are just like the natural numbers. But together, we still have a well order because if I start here, let's use a different color. If I start here and go left, eventually I'm going to run out. And then I will end up here, and I'll keep going until I run out. When I say eventually I run out of numbers in this first group, and I'll land in this second group. So this is a well order. Okay, the last example of a well order is pairs of natural numbers ordered lexigraphically. So let me remind you what this means. So these are ordered, wait, I didn't write this down correctly. Sorry. What I really meant was this, where this is lexicographic order. And what that means is AB is less than CD if A is less than C, or A equals C and B is less than D. That's what lexicographic order is. And this is how the words in a dictionary are ordered. The words in a dictionary are ordered by lexicographic order. The ordering is a little different. It's a little more complicated, in fact, because words can have basically any length. Here, we're just looking at pairs, but if we had two words, and we had cat and dog, cat comes first because the first letter C comes before D in the alphabet. If we had cat and cat nation, we would say that cat comes before cat nation because these are all the same, but now we have a blank, and the blank probably we'll say comes before any of the letters. So that is lexicographic order. So that was our third, or I should say, we have three examples. The natural numbers, this well order, and pairs of natural numbers ordered lexicographic. Those are three examples of well orders. There are many, many, many examples of well orders. We'll see more in the course. Okay, so we're going to stop here, and next time we're going to talk about ordinal recursion and induction.